Yeah, in today's class, we are going to see few more edge detection operators. So let us start with the recap of the previous class, and then today we'll see a few more edge detection operators, and they are mainly based on second order derivative. In the last class, whatever we have seen, that all was based on gradient, or you can say based on the first order derivative. And today we are going to see few operators which are based on second order derivative. Okay, so let us first briefly discuss what we discussed in the last class, and then we'll continue. So in the last class we discussed that in any given image, edges corresponds to significant local changes of intensity in the digital image. So wherever you are saying that in your given image, wherever you say that you have an edge, that means that particular place you have some significant local change in the intensity. Okay, and in that sense, an edge can be defined as a set of connected pixels that form a boundary between two homogeneous regions. Right? This also we discussed in the last class, that when we are defining the edge, these edges nothing but it is a set of connected pixels, and all these pixels have significant local change in the intensity. And if you connect all those pixels, the edge that you will get, that will basically form a kind of boundary between two homogeneous regions. So as we discuss in these 2 points, that edge is any edge point corresponds to local change in the intensity. So to detect the change, the simple way is to find out the gradient or the first order derivative in x direction and in y direction, and based on the gradient you just decide whether the change is significant change or it's not a significant change. Okay, so when we define our edge by using gradient, then this problem gets converted to actually computing the gradient of the image and then finding out the points where you have the high gradient. We discussed 2 approaches to compute the gradient. At any particular pixel, if you have to compute the gradient, this is one approach where to compute the gradient in x direction or in the y direction, we are considering, with respect to the pixel where we are computing the gradient, we are considering 2 pixels. If we are computing the horizontal gradient in the horizontal direction, we are just considering 2 neighboring pixels of the same row. And if we are computing the gradient in the y direction, then or in the vertical direction, then we are considering the pixels, neighboring pixels of the same column. Okay. So to compute the gradient here, you just need these 2 pixels. To compute the gradient here, you just need these 2 pixels or the intensities of these pixels. And then based on that, you can compute the gradient in x direction and gradient in y direction. And based on that, you can compute the direction of the edge or the magnitude of the edge. Okay. This was one approach. In the second approach, we saw many operators actually following this kind of approach, where to compute the gradient at a particular pixel, let's say in this case we are computing the gradient at this central point, at this central pixel. To compute the gradient at this central pixel, we did not consider only the neighboring pixels from the same row, but we also computed this kind of difference with respect to the pixel which is just above the pixel of consideration and below the pixel of consideration, and whatever total gradient we got with respect to all these 3 pixels, collectively based on that we decided the overall gradient at this central pixel. Okay, so that means we are computing the gradient at this pixel, gradient at this pixel, gradient at this pixel, and then adding that all, maybe you can say that taking average of the all 3, and then based on that deciding what is the effective gradient at this central pixel. Similarly, when we are computing the gradient in the vertical direction, here again we are computing the gradient not only at the central pixel but at 2 other pixels which are neighboring to this pixel on the same row, and with respect to all these 3 pixels, whatever gradient we get, based on that we decide the gradient of the central pixel. Okay. So based on this second approach, we saw a few operators like Privet operator, where we considered a 3 cross 3 neighborhood, and the operator to compute the gradient in x direction and y direction, it was defined like this. In case of Sobel, again, the operator was considering 3x3 neighborhood. And in the case of Sobel, the operator was defined like this. This was the gx, which is used for computing the gradient in x direction. This is gy, which is used in computing the gradient in y direction. Now, only the difference between Privet and Sobel is that in case of Sobel, we are giving more importance to the gradient that we get in the row or in the column corresponding to our pixel of consideration. To whatever gradient we get with respect to other two neighboring pixels, we get lesser importance to that. We give more importance to the central row or central column where our pixel of consideration lies. Okay. In case of Robert cross operator, in place of computing the gradient in the x and y direction, here the gradient was computed in diagonal direction. So this, with the help of this, we were computing the gradient in this direction, and with the help of this gy, we were computing the gradient in the y direction. So this is So here you get the gradient in this direction, which defines, let's say, gx, and here this gives you the value of gy. Okay, and in all these three operators, once we get the gx and gy, we can calculate the magnitude of the edge by using this formula. We can compute the direction of the gradient by using this formula. And to compute the gradient, we can use this simplified equation, which is, you can say in some sense, the approximation of this first equation. So by just adding the magnitude of the gradient that you have in x direction and y direction, also you can approximate the overall magnitude of your edge. Okay, let us see a few examples of these operators. So let us say we are applying this kind of operator, this operator, like where you are computing the gradient by considering only the pixels of the row or the column of the pixel of consideration, and then based on that you are deciding the edge. So here this is the given image, and at every pixel, using let us say the operator like this, where you have -1 here, 0 here, and 1 here, you have computed the gradient. And similarly, to compute the vertical gradient, you have used an operator like this, where you have +1 here, 0 here, and -1 here. Okay. So you can see wherever in the image you have vertical edges, that difference is visible in case of horizontal gradient. Because if you remember, yesterday I said that the direction of the edge is perpendicular to the direction of the gradient. So you see, if you just see, let's say this is a pole which is vertically standing here. So with respect to this pole, your edge is in the vertical direction. So you see, when you are computing the horizontal gradient, that is prominently visible here. Right? And similarly, all the features or all the pixels in the given image where you had horizontal edges, those edges are visible in vertical direction, because the direction of the gradient is always perpendicular to the direction of the edge. So like, for example, you see here you have a horizontal edge here, and that is visible here in case of vertical gradient. So now this is horizontal gradient, this is vertical gradient, but now to find out the final edge, you have to combine both the gradients. So you know how to combine. You can consider that this is your gx and the second one is your gy, and by considering all the corresponding values for respective pixels, you can apply this formula that you have here to compute the gradient and the magnitude of the edge. Okay, and normally whenever we compute the gradient, though we see here only horizontal and vertical gradient, but when you combine, you will see very similar kind of image. So if you observe these images, you see that at some places you see some kind of gradient, but actually corresponding to the original image, that particular place does not contain any edge. So to find out only the significant edges or the true edges, normally we do thresholding, and we say that if the gradient is above a certain threshold, then only we consider that particular place has an edge. Otherwise, we ignore that gradient. So to do this, Normally we'll perform thresholding operation, and in thresholding we'll choose a threshold t, and all the pixels where the gradient is more than t, we'll consider that, and wherever the gradient is less than t, we will set that as 0. So after thresholding, you will see that only the pixels which correspond to true edges will be only visible. Now the question comes how to check this threshold or how to choose this threshold t. So again, there is no fixed formula for this, though there are some approaches to compute an optimum threshold, but mostly this is decided based on hit and trial. Okay, so let us see one example. So let's say we have this image here, and we want to compute the edges here. So we have computed the gradient. Now in this case, what you see here is the gradient, the combined gradient. We have computed the gradient in x direction, we have computed the gradient in y direction for every pixel, and then we have combined that, and that is shown here. So now you can see here, since this gradient is combined, you are able to see horizontal edges here, vertical edges here, and even the edges which are not in horizontal and vertical direction, those edges are also visible. And the reason is that here we are combining both the gradient. So when let's say when we would have computed our horizontal or vertical gradient at, let's say, this particular pixel, we must have got some gradient in x direction, some gradient in y direction, and based on those x and y gradients, what you see is the resultant gradient. Okay. Now again, you see in this image there are a lot of places where in the true image you don't want any edge. Like say for example in this area or in this area, you know that these areas do not contain any edge. So we want to remove them. So how to remove those areas? So we will put a threshold. So once we put the threshold in the image here, only those pixels are visible which are above certain threshold. If they are below threshold, they have been set to 0. Now if we choose a low threshold, it is obvious to see that here there are some differences which are low, there are some differences which are very high, right? Like for example, wherever this butterfly has some feature, those features are at those places you have high gradient. So if you are putting a very high gradient, you will see that only these prominent features that you have here, they will be only visible. Other these small details will disappear. But if you keep low threshold, in that case you will find that these even smaller features are also visible. So as you see in this case here, we have chosen a lower threshold. So when you choose lower threshold, you see a lot of details, lot of information, a lot of edges visible here, or a lot of edges visible here, which are actually not the true edges. So if we, let us say, increase the threshold, we will see that now many of the false edges have disappeared. Only the true or very strong edges are only visible in this case. So by hit and trial, we have to decide what should be the suitable threshold so that maximum number of true edges can be obtained and maximum number of false edges can be removed from the image. Okay, so this is always a process of hit and trial or experimentation to decide the proper threshold. Now let us see few examples from the which are obtained by using standard operators. So this is the example you see here. Sobel operator has been applied on this image, on the left image, and what you see on the right image is the edge image obtained by using Sobel operator. Similarly, again the Sobel operator has been applied on this image, and what you see here is the obtained edge image when Sobel operator is used on the left image. Okay, so till now whatever we have seen, this already we discussed in the last class. Now let us see a few new operators. So in the last class, all the operators that we discussed, they were based on first order derivative, or we can say they were based on gradient. Now we are going to compute, or now we are going to see few operators which are based on second order derivative. Okay, and Laplacian operator is one of the prominent edge detection operator which is based on second order derivative. Now please remember, in the first order derivative or in the gradient we have a direction, but when we are computing second order derivative, it doesn't give any direction, right? It's not a directional quantity. So when we were adding to gradient, like say a gradient in x direction and gradient in y direction, that was a kind of vector addition. right? So that is why we computed the magnitude of the gradient. But here, the second order derivative doesn't have any direction. So to combine these two quantities, we can just simply add them. So let's say in the second order, in the x direction, your second derivative is this, and in the y direction, your second derivative is this, and you want to find out the combined effect, you can just add that. Okay, you don't need to do any kind of vector addition with respect to these two quantities that you get. So if you closely analyze this formula, if you consider, or let us first discuss this one. So if you consider that f is your image, then this first quantity give you the second derivative of at a particular h pixel in x direction, and this gives the second derivative at a particular pixel in the y direction. Now, when you are combining these two derivatives that you get from the image, and when you get this combined expression, if you closely see, this is actually nothing but a Laplacian operator. Because what is a Laplacian operator? Laplacian operator is a combination of partial derivative in second order partial derivative in x and y direction for any given 2D function. Okay, so that is why we say that this S detection operator is a Laplacian operator, because what formula you get here is similar to Laplacian operator. I just again write the Laplacian operator. So this standard Laplacian operator is this. This one, and exactly same thing you see here. This operator, I mean, if you observe this equation, you see that this Laplacian operator has been actually applied on the image. Okay? So that is why this this edge detection operator is called Laplacian operator for edge detection. If your image is fxy, I mean, if you let's say you say that you have I mean x and y both, which is hidden here in these expressions, in these two expressions when we are writing. More precisely, we can write the equation like this. So Laplacian of any given image fxy, if let's say it is lxy, then it can be said that it is equal to del 2 fxy by del x square, and then del 2 fxy by del y square. Okay, so you just get this value, and then based on this quantity, we can decide whether the pixel is an H pixel or not. Okay, so all these are the second order derivatives. So if you consider these derivatives in case of 1D, you will find that this equivalent operator can be written like this. If you have forgotten, you can just go back and see the previous lecture slide. You will find that the second order derivative was coming out to be like this, and in the x direction, and second order derivative was equal to this in case when the derivative was computed in y direction. Okay, and if you combine these two, this is in the x direction, this is in y direction. I mean, these are the equivalent operators, you can say, to compute second order derivative in x direction and in y direction. Now, if you want to combine these two, you can assume that at the rest of the places here, though this is a 1 class 3 matrix, this is a 3 class 1 matrix, but if you want to combine and want to make a combined operator, then you can assume that at the, this is again a 3 class 3 matrix where upper row and lower row have 0 values. Similarly, here this is again a 3 class 3 matrix where the left column and the rightmost column, they are 0, and when you are adding them, or when you combine them, you get actually operator like this, which is called the 2D Laplacian operator for edge detection. Okay. So now the process has become very simple. We can say if you want to detect edges using Laplacian operator, we have to just take this matrix, you can call this as a filter matrix, and you have to just filter your image using this operator or this filter matrix, and whatever outcome you are getting after that filtration process, based on that you can decide whether whether a particular pixel is an H pixel or it's not an H pixel. Okay, we'll see how to take that decision. So if you remember in the last class we discussed that when we are using first order derivative in the gradient image, we look for the places where you have high values, and those high values correspond to the h pixels. Okay. But when we are using the second order derivative, in that case, the pixels where you have 0 value, that corresponds to the edge. If you don't remember, I mean, you can just again I can draw. So if you, let's say your step is like this, and if you compute the first order derivative, the pixel where this transition is happening at that particular place in your first order derivative will find a peak. But if you compute the second order derivative, then the pixel where this change is happening at that particular place, you will find a 0 value. So if this pixel is plotted here, that you will find this peak corresponding to that pixel, and in the second order derivative, that pixel actually corresponds to this 0. So if we are using second order derivative or Laplacian operator, we just saw for edge detection, after applying the operator on the image, we have to look for the places where we have 0 crossings, or in a in other way we can say that we have to look for the pixels where we have 0 value in your filtered image. So first, to detect the edges using Laplacian operator, what we have to do? We have to first apply the Laplacian operator on the image, and then we have to look for the places where you have 0 values in the image, or more precisely, I mean, in terms of the definition or the discussion that we are having here, we can say that we have to look for the places where you have 0 crossings. Okay. Now, all these operators that we have seen, these operators actually perform very poorly if the image has noise. Okay. Till now, our operators were, not considering the presence of noise. But if, let's say, the noise is there in your image, these operators will perform very poorly. The reason is that since we are computing the derivative, or we are computing the difference, that difference is very sensitive to noise. So if the noise is there, the difference will be magnified, and your operator will show an edge there, at a particular pixel, but that edge may not be the true edge. Okay. So all the operators that we have discussed till now, they are very sensitive to noise. And second thing, they also generate thick edges. Okay. And if the noise is present, they generate false edge points, spurious edge points. Okay. And particularly the operators which are based on second order derivative, as the case with the Laplacian operator, these operators are very sensitive to spike noise. Right? Spike noise, or you can say one example of the spike noise is salt and pepper noise. So if your image has salt and pepper kind of noise, then Laplacian operator, which is based on the second order derivative, this will perform very, very poorly. So now what to do if your images have noise? So to perform the edge detection in noisy images, what is the solution? Solution is simple. So we have to first remove the noise, and then we should perform the edge detection. Now, how to remove the noise? So in the, I think 1 or 2 classes back, we studied a smoothing operation, which was actually used for removal of noise. Okay. So we can say here that if your image has noise, then you first smooth your image using some smoothing operator, and after that you perform edge detection. So for any given image, first you apply a smoothing operation, and after smoothing operation, whatever filtered image you get, on that you perform the edge detection and then get the edge map. The difference between edge detection and edge map is that here you don't have any thresholding, but when you are at the final stage, this is obtained by thresholding whatever output you, whatever image you have at this stage. Okay. So one of the popular filter which is used for smoothing is the Gaussian function. Okay. Other filters like mean filter, median filter, they can be also used for performing the smoothing operation, but in most of the cases you will find that Gaussian filter is being used for performing the smoothing operations. I'm sure you must be knowing the equation of the Gaussian filter in case of 1D, or the equation of the Gaussian in case of 2D. By using these formulas, in these two formulas, you see that you have a sigma, which is a parameter which need to be actually decided to compute the value of the Gaussian filter. Another variable you see here, which is the mean, which is not a very important parameter. You can assume that this mean is always 0. If you are considering any mean, any non-zero mean, this will only shift your filter from 0, 0 to some other place, but the values will be, same. The coefficient will be same. So this mu x and mu y you can just ignore. You can assume that they are just 0, 0. So the important parameter that you need to decide or for which you need to fix the value is the sigma. And by choosing suitable value of sigma and by using this equation, you can define the filter weights in case of 1D if you are using this equation, and if you are using the Gaussian equation for 2D, this one, here you can choose sigma in x and y direction, and based on the chosen sigma you can decide the filter weights, and you can get this matrix. Normally we will choose sigma x and sigma y same. So in most of the cases you will find that sigma x and sigma y are equal. So by using these equations we can generate the Gaussian these operators, and we can use these operators to smooth out our image. Now these are few examples. Here you see this is the input image, and on this input image a Gaussian filter of size 9 cross 9, which is obtained by using sigma equal to 5, has been obtained. So after smoothing you see this image. Now what is the outcome of the smoothing operation? We have already discussed. When you do smoothing in the image, your sharp features become blur. So wherever you have sharp feature in your image, you will find that those features will become blur. And as we just discussed, our edges are also sharp features. So when we are performing the Gaussian filtering or any smoothing filtering, we'll see that the edges also get smeared. They also become blur, which is a kind of actually problem of this operation. And to handle this, to overcome this problem, we'll see some solutions later. But at this moment, you can just understand that when you are applying the Gaussian filtering or any smoothing operation on the image, it removes these sharp features. So since noise is also a sharp feature, if you are applying smoothing on your image, we can assume that the noise also gets removed from the image. So once you have a smooth image, then actually you can apply the edge detection. First you have already smoothed the image, and once you have performed the smoothing operation, then you can perform the edge localization. What you need to do for edge localization? You need to now apply the operator, and whatever output filtered image you get, on that you put a threshold. And normally when we put threshold on the image, we get a thick image. Okay. The reason is that, if you go back and see this image here, if you let's say observe this particular part, you can very clearly see that if you apply any threshold, you are not going to get just 1 pixel wide edge here. It will be a thick edge because there are many pixels. Let's say just consider the peak of this part, this one. There are many pixels which will satisfy actually the criteria that you are going to put for threshold, because most of these pixels are having similar kind of intensity. Okay. So, and normally when we look for an edge, we look for an edge of 1 pixel width. So to convert thick edge to thin edge, we perform thinning operation. So that's what you see here. We have a thinning operation here. First we have thresholded our image, and in that thresholded image we may have some thick edges. So to convert those thick edges to thin edges, we perform thinning operation. And this thinning operation for timing you can just ignore. You can just assume that this is actually converting a thick image to 1 pixel wide, thick edge to 1 pixel wide edge. But how it is performed, we are going to see later. Okay. Now let us analyze what is the effect of sigma. We saw that if you are using the Gaussian filter for doing the smoothing, then sigma was an important parameter there. Now what is the effect of sigma if we choose a small sigma or if we choose a big sigma? How it is going to impact our image? So and there are multiple names for sigma. Sometimes we say we call it as a scale, or sometimes we call it as a width, or sometimes we call it as a spread, but all of them, I mean, refer to the sigma used in that equation. So if we are choosing a small sigma, this basically mean, if you remember, you had a, I mean, let us consider the 1D case, and then based on that you can extrapolate for the 2D. So if in case of 1D, if your sigma is big, or let us let's consider first this case where this sigma is small. When your sigma is small, you will find that this peak will be very sharp peak. So this basically says that suppose you are going to convert the values obtained from this equation or this function that you have here, and let's say you are going to get the 3 cross 3 operator from this, or 1 cross 3 operator from this. So you will find that, let's say you have a sigma is very sharp. So then you will find a very high value here, but very low value at these two places. But if your sigma is high, you will find that this peak will not be a sharp peak. This peak will be a kind of a peak like this, a wide peak. So in this case, if you, let's say, try to get corresponding 3 values of your filter, you will find that whatever you are going to get here, this will be very similar to what you have here and what you have here. Right? You can, I mean, see that from this equation, because the value at this point and value at this point and value of this point, they are not very different. They are very same. Okay. So, and if you are visualizing this the same thing in 2D, then for a small sigma, if you are, let's say, creating a I mean, as you see in this example, it is creating a 30 cross 30 filter. So if you are creating a 30 cross 30 filter and your sigma is small, you will find that in that 30 cross 30 region, at the center point, you will have high values, and at rest of the places, you will have very low values. So that is why you see at the center, you see bright spot here, and on the periphery, you are seeing the 0 values. And if you are increasing the sigma, you will this white dot will actually increase. So you see you have a more sigma here. So this the size of the filter is same 30 cross 30, but now since the sigma is more, this white portion has got increased. And when your sigma is further increased, you see that the white portion is further increased in the image. And in terms of smoothing, basically, if you are increasing the sigma, or if your filter is changing like this, then it gives more and more smoothing. You can say that if sigma is high, you are going to get high smoothing. If sigma is less, you are going to get less smoothing. And what is the meaning of high smoothing and low smoothing? High smoothing means most of these sharp features will disappear. In case of low smoothing, only the features where you have low difference, they will disappear. But the features where you have high difference, they will actually they will be still there. Okay? So as you see here, when you are moving from this side to this side, in the first case, let's say when you smooth this and got this image, still in this part you are able to see some features. Let's say suppose some grass or something was there here, so you are still able to make out something here. But when you increase the sigma, those small features have all disappeared. So if the sigma is less, you will be able to retain the big features of your image. Small features may disappear, but if you are increasing the sigma, for high sigma, you may even lose the features which are big. So as you see here, when you have a very big sigma, the small features have completely got lost, but even the boundaries of the big features, they have also got very much smelled. Okay. So in summary, if you are having high sigma, you will get more smoothing. That means you will be only able to retain the big features. Small features will certainly disappear. If you are having small sigma, certainly you will be able to retain the big features, and depending upon what sigma you have, you may be able to retain small features as well. So if your image has, depending upon what kind of noise your image has, suppose your image is very highly noisy, then maybe in that case you need high sigma. But if your image is not that noisy, then you may just choose a small sigma. Again, what value of sigma need to be chosen is again a matter of hit and trial or experimentation. Okay. Here we see examples of the effect of sigma on derivative. So when your sigma is small, 1 pixel, you see some images here. But when you make sigma big, the images that you see, the edges that you see here, they only correspond to big objects. Small objects have all dissipated. For example, you can notice what is happening in this area. All the features of this DoG are appearing here up to some extent, but all the small features that you have with respect to the grass or the background, they are not much visible. Okay. Okay. So larger value, when you are choosing the larger value of the sigma, large scale edges only remain in your image, so they are only detected. If you are using a small value of sigma, then finer features are retained, or you are able to retain the smaller features also, and in that case the finer features are obtained. Okay. So when you are saying finer features are obtained, obviously the larger features are also obtained. But when you are saying larger features are obtained, in this case you may lose the finer features. Okay. So now what sigma to be chosen? This actually depends on the application, what you are looking for. For example, in these images, let's say you are looking for only the on the tree boundary. You are not looking on the details of every leaf. Then you can choose a big sigma. But if you are, let us say, you are interested in all these small features, or even on these leaves, all these small features that you have here, so then in that case you should choose small sigma. Okay, and in some cases we want small features as well as the bigger features. So later we will see we even analyze our images in multiple scales. So we may analyze our image by choosing a high sigma to detect bigger features, and we may analyze our image with respect to small sigma and to detect the small features in the image. Okay. So multi-scale processing is also done. But let us at this moment restrict to ourselves to only one level of processing. So depending upon the details, and since here we are interested to use Gaussian filter to remove the noise, so depending upon how much noise you have, we can suitably choose our sigma. If your image is very noisy, you can choose high sigma. If your image is not very noisy, you can choose a small sigma. Okay. So based on this, we have a few operators which are based on second order derivative. Those operators we will see in today's class. We will try to see quickly the LoG operator, and later in the next class we will see the Kani edge detector, which is again uses the Gaussian filtering and first order and second order derivative computation. So LoG operator is based on Laplacian. And as this is the name of the operator is Laplacian of Gaussian. That means you are going to use here Gaussian, and also you are going to use Laplacian. So that means you are going to compute the second order derivative. But now till now what we have done, whenever we said that we have noise in the image, what we did, we first applied the smoothing operation on the image, and then we computed the gradient if you are using the first derivative, or the Laplacian if you are using the second order derivative. But in case of LoG operator, it was actually proposed by Marr and Hildreth. This is also called Marr and Hildreth operator. In this operator, Marr and Hildreth actually they combined the differentiation and smoothing operation. So in LoG operator, we are not performing Gaussian smoothing separately and then the derivative computation separately. These two operations are actually combined here. And what is the logic behind combining these operations? So if you analyze these two operations, the nature of these two operations is actually very opposite to each other. For example, in case of smoothing, you are trying to suppress the sharp features. But in case of edges, you are trying to highlight those sharp features. So if you are applying them one by one or one after another, these two operations actually opposed to each other. So that is why these people actually suggested that we can combine these two operations and then apply them together to nullify the effect of this opposing to each other. And why is it possible? Yeah. So before that, let us. So since this LoG operator is based on second order derivative, because this is Laplacian of Gaussian. So in when we are using this operator, we are again looking for the zero crossings because this is second order based on second order derivative. So first we will use this operator on the image, and then we'll look for the zero crossings. There are two limitations of this operator. As at the beginning I said that using the second order derivative, you cannot compute the gradient magnitude or the strength of the edge. You cannot compute that, and also you cannot compute the orientation of the edge. Both these things cannot be computed. You can detect the edge, but you cannot detect how, or you cannot find out how strong that edge is and what is the direction of the edge. These two things cannot be obtained if you are using the second derivative, any operator based on second derivative. And since Laplacian is based on second order derivative, so that is why you are not able to detect those two things here. Okay. Now let us see why we are able to combine these two operations. So so what are the two operations we are talking about here? The edge detection and the smoothing. So normally what we do in our practice, if let's say we have to apply first order derivative on a noisy image, first we use Gaussian on the image, and whatever the filtered image we get, on that we apply this operator H. Let's say this is edge detection operator. Okay. Similarly, we do in case of 2D, we have image. On that image we have applied the Gaussian, then we took the first order derivative, and then we took the second order derivative. Okay, this is the normal procedure. But as we see that if you are, and this symbol that you use here, this is actually for the convolution. In convolution, if you have this simple equation, this can be written like this. You can combine G and H first, and then you can apply that on I. This is same. Okay. So similarly, in case of second derivative also, you can rewrite your equation like this. And when you rewrite your equation like this actually becomes this filter applied on image I. Now what is this filter? Or what is this part? This is actually the second derivative of the Gaussian. So this equation basically says that in place of first computing the smooth image and then applying the derivative on that image, you can get the same thing if you first take the derivative of your Gaussian 2 times and then apply on the image. And that's what exactly the Marr and Hilder suggested, that in place of first doing the smoothing, first compute the second derivative of the Gaussian, and second derivative of the Gaussian is nothing but Laplacian of Gaussian. So this operator becomes the LoG operator or the Laplacian of Gaussian operator. So you first compute this operator and then directly apply that on the image. And since this is again based on second derivative, we are looking for zero crossings. If you just see how the operator will look like in case of 1D, we are seeing this here. So this is the Gaussian function. When you take its first derivative, it looks like this. When you take second derivative, it looks like this. So edge detection is nothing but applying this operator on the image. Now let us consider the case of 1D, and this can be again extrapolated for the or extended for the 2D case. So this is your given function f. This is the operator, Laplacian operator, and we are applying this Laplacian operator on this. We are applying this Laplacian operator on this this intensity profile, and we are getting this output. Now to look for edge pixel in this output, we have to look for the zero crossing. So you see zero crossing is happening here. So this point corresponds to the edge location in this 1D profile. Okay. In case of 2D, your Gaussian function will be like this, and if you take the if you perform the partial derivative in x and y direction 2 times to get the LoG operator, the equation will be like this. And by choosing suitable values of suitable size of the filter and suitable value of sigma, you can define the filter matrix. So in case of 2D, the filter matrix comes out to be like this, and here you can choose any size of the filter and any value of the sigma. But one thing you need to be remember that the total sum of all these values should be 0, so that when you apply this filter on planar region, you don't get any edge. You get just 0 value there, right? Because wherever you have plane region, there shouldn't be any edge detected. So if you are keeping the total sum of these values as 0, then it will guarantee that if you are applying this operator on planar regions, you will get 0 value. Okay. So when you are applying the LoG operator on your image, and again, just for simplicity, consider the 1D profile of your edge. So when you are on one side of the edge, and more precisely on the darker side of the image, actually you will get the filtered value positive. When you are on the positives, I mean the lighter side of the edge, you will get positive value. You can see that here. So corresponding to this part, you are getting a, or I mean when you are on closer to edge, but on the negative side, you are getting positive value. But when you are on the negative side, when you are closer to edge on the positive side, you are getting negative value. So that's what happened when you are applying the LoG operator, and that's exactly we are stating here, that you will get positive on the darker side, and you will get negative on the lighter side. And more precisely, you can say that on the long edge, so you have, let's say, the edge like this. So on this particular part, you will get 0 value. Right? The first point. You will get positive when you are near the edge. You will get negative when you are near the edge towards the lighter side. And in between this positive and negative, somewhere you will get 0, and that will actually correspond to the edge point, right? Because that will be the 0 crossing. One thing you can notice here, that using the second derivative, we cannot find out whether an edge is a high edge or a strong edge, or it's a weak edge, because in this case we don't have any we don't have any magnitude of the edge, right? Because if you just consider the example, let's say you have an edge where the intensity difference is only this much, and you have an edge where your intensity difference is this much. Okay, but in both the cases, the edge is detected by 0 crossing. So corresponding to this edge also, in your when you are applying this filter, you will get a 0 value, and corresponding to this edge also, you will get a 0 value. But very clearly you can see that this particular edge is a weak edge because the difference is not very high here, and this particular edge is a very strong edge because the difference is very high here. Right? But using LoG operator, we cannot differentiate this. So there is some way to handle this situation, and that actually can be done by considering the values that you the values that you get for these peaks. What value you get when you are on the negative side, on the darker side, closer to edge, and what value you get here when you are on the lighter side, closer to the edge. You will see that these peaks will be high if this difference is high. If these peaks will be of low height if the difference is low. So based on these the height of these peaks, we can actually decide up to some extent whether the edge is a weak edge or it's a strong edge. So one more thing you can notice here, that when your peak is very high, you will get a profile like this. So if you connect these two points, this line that connects these 2 points, this will have a high slope. But if this peak is a very, these peaks are of low height, then these peaks will be like this. So if you connect these peaks by the line, this line will have low gradient. Okay. So based on the value of this gradient, we can actually compute whether the edge is a strong edge or it's a weak edge. So exactly same thing we apply here. And to compute the slope, there are multiple possibilities. In some cases, you may find when you are computing at a particular pixel, on one side you may find positive value, on one side you may find negative value. You may not find anywhere 0 value in between this plus and minus. This is just because you are computing in the discrete domain. Sometimes you may find positive on one side, 0 on negative on other side, and 0 at the middle. and similarly a minus on one side, plus on another side, and 0 at the middle. But there might be some cases where when you are transiting from plus to minus or minus to plus, you may not encounter 0. So we don't need to worry about that. Whatever positive and negative values you are getting, corresponding value you can assume that is A and B. So whatever plus value in all these 4 cases, whatever plus value let's say we are getting, we can assume that A, and whatever minus value we are getting, we can assume that as B, and we can compute the slope by computing mod of A plus B. Okay, and depending upon what value you get here, you can apply a threshold on this value to decide whether corresponding edge is a strong edge or it's a weak edge. Right? So up to some extent you can manage or you can detect the strength of the edge by using the slope, but still we cannot detect the orientation of the edge. This doesn't tell anything about the orientation of the edge. So you know that when we are computing LoG operator, we have to compute the second order derivative, and second order derivative is costly as compared to the first order derivative. So there is an operator called DoG operator, which actually can approximate LoG operator. And DoG operator is actually the difference of Gaussian, which is based on first order derivative. So since we are able to get able to approximate LoG by using DoG, many times we prefer applying DoG operator in place of LoG operator, because LoG is based on second order derivative and DoG is based on first order derivative. Okay, and how we are saying that both are same, that we can actually mathematically, I'm not explaining that here, we can understand that with the help of this example. So if you remember from the previous slide, our LoG operator was like this. Okay, only in this case, in this time I have just inverted the peak. If you see here, the peak was downward, only the peak has been, yeah, this was our LoG operator. Here the peak is towards negative, but here the peak is up. Okay, that is the only difference, otherwise they are same. So if you are considering our LoG operator like this, and let us consider 2 Gaussians. Let us say our first Gaussian is this red curve. You know that you know the equation of the Gaussian. Gaussian looks like this. You have 0 and then you go up to a peak and then come down to 0. Similarly, this yellow curve is also a Gaussian. Here also you see the similar nature. Only the difference between the 2 Gaussians is that they are obtained for different sigma values. Wherever you have sigma low, you will have a high peak. We just discussed. Wherever you have sigma high, you will have a low peak. Low and wide peak. When you have sigma low, you will have a high but a very wide peak. A very narrow peak. Okay, sigma low means narrow and high peak. Sigma high means wide and shallow peak. So we have corresponding to those 2 sigma values, we have red and yellow. Now if you take the difference of these 2 Gaussians, we get this blue curve. Okay, we are just subtracting corresponding values of red and yellow Gaussians, we are just subtracting them. Okay, so we get this blue curve. Now if you just compare this blue curve with this LoG curve here, we see that they are very similar. Okay, so since we see that this difference of Gaussian is can be considered similar to what we get in LoG, so in case of using the LoG operator, we can approximate that using DoG operator. Okay, so normally in place of LoG, we will prefer using DoG because that is based on first order derivative. Okay, so let us stop at this moment. In the next class, we will discuss canny edge detection. Thank you.